Hey guys, I think we can start now. Uh, uh, Welcome, and today I will be presenting this beautiful paper on emerging properties in self-supervised vision transformers. So, if you are familiar with the transformer architectures and how they have termed the domain of natural language processing, then came vision transformers, which took the leap from BERT in NLP and translated the same work, almost similar work on vision tasks. This paper focuses on what kind of meta learning is being uh, learned by the internal layers of the vision transformers, and more so specifically when we train it on self-supervised methods versus when we train it with supervision. So, uh, so these are the people who might find this work very interesting. Notably, the fetal gender masking project, I think that they are the ones who would find it interesting because they have very less data. The number of unlabeled data for them is very less compared to. Uh, yeah, I think I made a mistake here. It should be double less. Okay, so the number of labeled data, they have very less labeled data compared to. Uh, sorry, so they have a lot less labeled data compared to the amount of unlabeled data they have. The implants project that I'm currently working on, we have a lot of unlabeled data, but very less labeled data, right? Maybe casual inference, I'm not sure what they do, but yeah, they could look into this project as well. So if you are someone who has very less labeled data, a lot of unlabeled data, you do not want to train a model from scratch on those unlabeled data. You want to use out of the box pre-trained models such as VIT or any other ResNets. Then yeah, this is the paper which might give you some insights into how this might be useful for you. So in brief, this is a self-supervised method. So this is a self-supervised method, uh, and it beats the state of art in computer vision on various tasks. We will discuss what tasks they focus on. But their major focus in terms of the architectures are two only, the VIT and the ResNet 50 architectures. They compare it with supervised training method and the self-supervision that they experiment with. Their metrics are mainly focused around linear classification and nearest neighbor classification. Right? So yeah, so if you look at some of the results from this paper, this is what it says in nutshell. Uh, so if you have this picture that you are seeing over there, like some wine bottles and some bananas, then these are some of the output heads. I'm assuming that you're aware of the transformers because I think the initial two reading groups did cover that in brief depth. So if you suppose you input this input image to the transfer to the network such as VIT or ResNet, uh, then you can understand from this four images that are shown here that and these are the attention weights of the last layer of the transformer architecture on this image. So it says that different heads or different parts of the last layer of the network understand different features of the image very specifically. So look at this one. This understands about the labels, right? This understands about these are different heads. So you can extract one head and apply it to your own task if you want. So if you want to have a banana detector, then you can extract this head and say, okay, I want to use this head particularly for banana detection. Uh, uh, these understand more so about the bottles as such, and these probably understand about different brands that are put on top of the labels. You can see over here as well, right? So not just the bottle, but the brands as well, the printed labels. And you can see across different results that are shown here, and we will talk about it more in depth later as well. So in a nutshell, what this paper tries to do is tries to replicate or tries to come up with a very similar pipeline that BERT has. So BERT is a pre-trained model that you can use out of the box for any downstream NLP task, and it performs pretty well across different tasks. So they try to come up with a pre-trained model that are trained on self-supervision, and that you can translate it for your own task. As I said earlier, that maybe fetal gender masking or implant identification or causal inference can take it out of the box. So this work comes from Facebook AI. Very similar work has come from Facebook AI. More so, if you talk about this architecture that came few months back from the same team in the same lab from Facebook, and this paper is also based similar, the similarity between this architecture and the one that is mentioned in this paper are very much. You can so this is one of the earlier architectures that came named Suave. So and this is Barlow twins. So to compress everything, what is the similarity between these two architectures is you have an input image. So I'm taking these Barlow twins and we will extrapolate it to our DINO work as well. So you have an input image. You apply different transformations on those input images. So you apply, let's say, flipping on the left side for this, flipping 90 degrees, flipping 45 degrees, or whatever data augmentation technique you can use. And you get two different representations of the image. You pass it through a network and you get a representation, let's say the last layer of your network, right? And these are the different representations of the two different transformations of the same input image. And you try to find the similarity between these two representations. So your buck stops here, and then you try to find what is the similarity between these two representations of different transformations of the same image. And your objective is you want to learn a model theta, this one, which is invariant to the transformation or which is resilient to the transformations that you bring in this system, right? So your objective is to learn identity here, and there are different objectives. So you can see that in Barlow twins, their objective is to learn identity matrix, and in Swab, their objective is to learn a different. They deploy a different objective to learn. In Boyle, they have a different objective to learn. They use a prediction and then negative log likelihood to find the similarity between these two different representations. But in a nutshell, you want to learn theta that is invariant to different transformations you do on the same image, right? This is during the training phase, during the testing phase, and that we will see how you use the unlabeled data to basically label it using this architecture. Yeah, so some of the findings, like, yeah, we'll see if you're aware of how VIT works. If you're not, then I can go through the internal workings of VIT in brief. Are you okay with that, or should I move on?
Well, I would like to hear that if you can explain it.
Okay.
Okay.
Yeah. So if you're aware of how BERT works, so you have an encoder. So you have a encoder architecture, right? And I'm trying to draw the similarity between BERT and what VIT does, right? And then how VIT adapts it to DINO, right? So and then you have different words in your sentence, right? So I am a rider. Let's say I'm a bike rider, right? So there are words like I am a bike and a rider, right? And you draw different embedding representations for these particular words. So I will be represented with, let's say, 256 long embedding vector, right? And you feed these embeddings, you concatenate these embeddings, you align them with position encodings for each one of them, and then you concatenate everything and you start feeding sequentially these to your transformer encoder, right? And at the end, you have you do apply what is called a CLS classification that is used for depending on your task objective. Let's say you want to do sentiment classification. Then you take this input image, you stack it with classification CLS token, and then at the end you will be getting some representation for the CLS token that you use it for classify. Then you put a classifier on top of it and see whether it is neutral or negative or positive, right? So this is the basic, like in short, this is how BERT was trained on. But what the issue with images is you do not have a very sequential ordering in images, right? You have a 256 by 256 image. The question arises, how are you going to make it sequential? Because transformers take sequential input and you have to provide it, you have to preserve that sequence as well. So the innovation that came with VIT and before that to Data from Facebook AI, VIT from Google. What they did is they chunked the image into multiple sections and they vectorized the image. So now you have, let's say, 8 by 8 chunks of the whole 256 by 256 input data, right? And you sequentially arrange these inputs. So what you do is, let's say this is 1, this is 2, 3, 4, and so on. So now, just like what we have as I am a bike rider, you have these different sections of the image that are sequentially arranged, and you feed so 1, 2, 3, 4, 5, and so on. And then you first you vectorize it, you convert it into embeddings, and assign the positional encodings just like here, and then you feed it to the encoder. So the innovation that came here was this chunking of the image data into multiple sections and then feeding it into the network, right? The experiment, the way you chunk your data is very much representative of how much you consider as one word, right? So if I consider I am as one word, that would be different compared to if I consider I as one word and am as a different word. So the same goes here, but more refined. Do you consider this as one element or do you consider this as one element, right? These are two different representations of the image, but they have different knowledge depth into them, right? So this is what they experiment in here as well. They start with 8 by 8 chunking as well as 16 by 16 chunking. And they do find that, though there is a trade-off, we will see later on that how does computational overhead come with 16 by 16 chunking or 8 by 8 chunking, right? But if you want to have good accuracy, then yeah, 8 by 8 chunking is what you use, which is more refined. As you can see that if I use I am as a single word, that is compressing the knowledge, maybe disregarding some of the knowledge in there, compared to if I use I as one word and am as a different word, right? Same way, 8 by 8 contains more knowledge compared to 16 by 16. Yeah, so that was a brief intro into what VIT does. So the experiment was to experiment with 8 by 8 chunking, 16 by 16 chunking. They also do experiment on 5 by 5 chunking for VIT. So right into what kind of parameters and what is their structure of the experiments is. They experiment with ResNet 50, the same VIT base 8 and VIT base 16. Both DIT and VIT have very similar architecture but different implementations, so we will use these things interchangeably. They run this for 3 days on 16 NVIDIA V100 clusters. So that's a lot of computation required if you really want to train it on the data set. They primarily train it on ImageNet. So ImageNet with no label, generally we know ImageNet has labels. So they use it for inference, the labels, but they do it in self-supervised manner with ImageNet data without the labels. Yeah, so that's the important thing to note down here. And then they, once they have trained it on ImageNet, they extrapolate that on various different data sets like Google landmark detection task, the image retrieval, and then copycat detection and video segmentation, right? Over here, Davis 2017. So like what we see nowadays in most of the transformer papers is this peculiar thing about nothing very new in terms of architecture. So you're not going to see like I have a ResNet and then there is a DenseNet and whatnot. The majority of the innovation that we see in this paper and in similar ones as well is the hyperparameters. So they come up with very unique set of hyperparameters that does exceptionally well across these data sets and on these tasks. We have these tasks here, image retrieval, copy detection, and so on. Right? So just to mention, and it is a difficult task to do actually. So I mean, coming up with these parameters like, okay, I'm going to scale the learning rate in this way, and I'm going to use a cosine scheduler for from 0.04 to 0.4 only, not anything else, right? And if I'm going to clamp this, I will talk about softmax temperature. I'm going to clamp the softmax temperature for only the teacher, not the student, right? So these are the unique things that are mentioned in this paper, uh, which makes this paper distinct actually. So this is the most important part of, maybe the most important part of this paper, the set of different hyperparameters they use to train the network. Right. So yeah, coming back to the point of how you are going to train it, right? So as I said earlier, you have an input image. Uh, so one innovation they do is displays what kind of transformations you are going to apply on uh, these two sets of images. So let me, I will briefly explain and then maybe I can ask a question to you guys. What do you guys think? So you have an input image and you do different transformations on the input image. Uh, you take two different representations. So you have a model, let's say VIT, let's say base 8, right? And you make two different copies of the same VIT base 8 at the beginning. Now, one of them you call as a student, that is S theta, and the other one is T theta, right? Uh, and then the rest of the architecture seems very similar, except so the whole architecture is same. You have the same VIT base 8 here. You put one image to the student, one image to the teacher. You pass it through. You put a softmax layer on the top, get the probability distributions at the end, both for the teacher and the student. But what the distinction here is, you do not train the teacher. So the teacher is never trained. So so there is no back propagation here. The gradients do not flow in the teacher. So the teacher is always learning from the student. The teacher is not learning on its own. So teacher is the accumulation of the knowledge learned by the student. The back propagation only happens for the student till here. Yeah, till here only. Right? And then at each iteration or maybe at each epoch, the weights of the student are added to the teacher in an exponential manner, right? Uh, so I would like to know what kind of transformations you guys think you can deploy on this teacher and the student so that the teacher is always performing better than the student. Okay, one thing to know, okay, so the loss is always compared between the student performance and the teacher performance. So the teacher, the output of the teacher acts as a label for you, inherent label. So your label should always be better than your prediction by the model. So one thing that you can do is you can do different transformations on the same input data. But what kind of transformation do you think you can deploy on these two setups, on these two lines, here and here, which makes the label always better than the student? Maybe I can wait for a minute. So you have an input data. You apply two different transformations. Let's say, right? What kind of transformation you guys think would be suitable for the student and the teacher?
I don't know, maybe masking some region of the images of the image fed to the student, maybe. I don't know.
Okay, yeah, I mean, That's in line with what the paper did. And
Oh.
that's not exactly, but yeah, it's in line. The ideology is same, similar to that. Anything else?
Maybe some random noise applied to the pixels.
Okay, that could be one. Okay, yeah, that could be one as well. But they did not experimented with that in this paper.
Okay.
What they did is what you said, masking some of the portion of the image, right? But how they did it is they do not mask the portion of the image and feed the same input. What they do is they take different sections of the image. So they crop the whole image into multiple sections. But there is a difference between, so you crop, let's say this portion of the image. So this is one portion that is fed into the student. Maybe this is another portion that is fed into the student. The difference, the innovation that they came up with for the teacher and for the student, they use different set of pixel density to feed it. So for the student, you always feed all different sections you can come up with. So for ranging from less than 50% of the pixels to more than 50% of the pixels. But for the teacher, you always feed more than 50% of the pixels. So in this case, suppose if my input image is 100 by 100, 10 by 10, then we have total of 100 pixels, right? And to the student, you can feed ranging from 1 to 100 pixels. But for the teacher, you always feed from 50 to 100 pixels, right? So the teacher always gets more data, that is more knowledge, and they're always cropped from the center. So you always take a crop from the center, around the center, with more than 50% of the pixels, right? So the teacher always has more data, more knowledge about the input data compared to the student. So it always produces labels which are superior to the ones produced by the student. Yeah. So I think okay. I will come back to this. I need to maybe I can cover this one first. So some of the so that was the data augmentation that I was explaining here. So what kind of data augmentation you can come up with, and some of the data augmentation that they do is, let's say, jitter the color and then they crop it. Maybe Gaussian blur, as Matthew was saying, right? They do that as well. I forgot, and then they crop it. So cropping is a must, but these are the extra augmentation that you can do on top of it. Solarization, multi-crop, and bicubic interpolation, they all do that. But there is a very unique thing that they do apart from providing more than 50% of the pixels to the teacher compared to the student is always take the loss from the best with the worst. That way the student always gets more penalty and is bound to learn better in the next step. So what they do is you have two different augmentations, augment one, and let's say one is cropping with 50%, one is cropping with, let's say, 30%, right? And then you pass it to the student. GS is the student and GT is the teacher, and you get two different representations for the student and the teacher. And GS and GT are this architecture. So this whole thing is GS, and this whole thing is GT. And what you do is you pass it to what we call as head. And if you can look here properly, then you see we are passing one augmentation. So T1 is compared across S2. So this is how it is compared, and these two are two different augmentations. So with the same input image, you are comparing, let's say, 50% of the pixel density with 30% of the pixel density, 50% going into the student, 30% going into the teacher. Right? So two different augmentations. So and they are mismatched, so that there is a lot of distance between these two representations, which force the student to learn better. So the loss will be more, and the gradient flows in a much more better way. And then very simple backpropagation, updating the parameters with the SGD. What they do next is what we call uh, as collapse prevention. So what collapse means is you have an input data, and you try to make a very trivial representation of the input data. So your model doesn't learn anything much, but both the student and the teacher starts being very trivial, right? A very trivial representation would be without any weights, right? Just unity weights and everything, the input layer and the output layer remains the same. That's a very trivial representation, right? And that way you can reduce the distinction between the input between the teacher and the student representation. So essentially your theta s and theta t are like identity metrics. That's a trivial representation. You disregard that by what they call as centering. And what basically happens in centering? Maybe I have to respect the time here. Maybe I have 5 minutes more. Uh, okay. So they prevent collapse. They prevent collapse by centering and softening. More so by centering. So this is centering. What they do is they add a different parameter which is also exponentially learned in an exponentially moving average fashion. So you start it with some value and then you exponentially move it with so B is the batch size, G theta is, as you see, the output of this is G theta, the output of this one. And then you move it across different batches, different iterations, and you keep accumulating it. So apart from this input, whatever input is going on, you have another addition on top of it. This as well. This itself is also a moving average. So it has a register. You can store the register C over there, and you can keep adding it in an exponentially moving average, and which is weighted by the output of G theta, as you can see here. So what this does is it forces the architecture to depart from identity. So now the student, because the student is faced with a better label, it will never restrict itself to identity matrix. So your collapse is prevented this way. And yeah, softening is just like usual softmax layer with temperature. So they add a temperature which is greater than 10, greater than 0, and then they take negative log likelihood as a loss. Okay, we can skip it. It is just like classification layer on top of the output of the GS and G theta that we use. If you look at the results, then we see that basically DINO trumps everything that came before it. And it trumps more so in self-supervised learning. So what they basically say is the features learned by self-supervision is superior to the features learned by supervision. Right. So if you have a label data and you train DINO with the label data, it is bound to, at least in their experiments, it is bound to perform inferior compared to if you train it with unlabeled data. Right. And you can see in these results here. So these are with these are with supervised ImageNet data, and this is trained with unsupervised unlabeled ImageNet data basically. And they both are VIT base 8 architectures. But you can see that the unsupervised or self-supervised version is able to understand the objects much more clearly compared to the supervised version, right? So next time, if we have like on a light note, if you have complaints about we do not have enough label data, then yeah, this could be like a benchmark to say that we do not need label data more so if we have a very well trained models such as DINO, right? So if you have unlabeled data, let's say implant identification, or let's say fetal gender masking, you have very less data, less labeled data, because the expert labeled is very rare, and you have a lot of unlabeled data. You can take this model out of the box, the pre-trained model on ImageNet that is available by Facebook, and you can fine tune it on your own unlabeled data. So you don't need to label it, and you can apply that to label the data now. Can anyone come up with how are you going to label the data? Maybe I'm exceeding the time limit here, but how are you going to label the data? So you have, okay, maybe I can see. So you saw here, right? You had two different augmentations, and one of the augmentation, and okay, maybe more so here, yeah. So you saw here that there are two different representations of the input data, and what you're basically trying to do is you are trying to learn a representation which is identity. So these two different representations are same, right? So if you have a single unlabeled data, how are you going to find the label of this unlabeled data? Can you come up with maybe a strategy? So let's say you have two images, right? Image A and image B. You have a label for this image. You don't have a label for this one. So you have to label this. How are you going to do that with, let's say, this architecture? Forget about this part, but how are you going to do that?
Like maybe the most similar representation from the unlabeled.
Yeah. Okay. Okay. So most similar representation, right? So you are trying to. Okay. Yeah. So what you are saying is you take the representations of A and representations of B, and find the representations which are highly similar and assign the label.
I mean, okay. No, never mind. I thought like we compare it to that representation of different labels and then choose the closest one.
Yeah. Yeah, that could be a strategy. So yeah, actually that works. So what you do is you break this portion. So instead of feeding the same image, you feed two different images now. So you feed A here and you feed B here. And because these F theta are same, you can see here, right? You can find two different representations as you mentioned, and find the representation. You can just keep feeding B1, B2, and so on, different label data, and find the one which has highest similarity with A and assign the label. So whatever the label of, let's say, B10 is the highest similarity that finds with A. So whatever was the label of B10, you assign that to A. So that's how you generated a automated pipeline to label unlabeled data with self-supervision. So you do not have to go for expert label data, or you don't have to wait for the label data in your pipeline. Okay. Yeah. One more interesting thing to note here is that the model, the DINO architecture, was never trained for image segmentation, right? But if you look at the final layers of the VIT architecture, it definitely understands segmentation, right? So it was trained on classification task because it was trained on ImageNet. But if you look at the last layers, then it understands the different regions of the image, and more so in a very refined manner, actually. So you can see the face of these, whatever it is, the horse or whatever, right? So face of the horse and the white region of the horse, maybe the strap of the horse. These are all uniquely understood by the architecture, which was never a part of the input data. So input data contains only classification task. And if you look here, this is a black and white kind of image, maybe a winter day. And even in this case, it is able to distinguish between this. So it's like you can treat it as black and white image. So it is not only about the density of the image as well. So it doesn't require a very high density RGB data, but a black and white data as well performs equally good. Right? Yeah. So this was a video. Maybe I don't know if I can play. I can't play here. So this was a video of a dog running. So as the perspective of the image changes, the model also is able to understand what is in focus in the particular frame of the image, right? So the background remains almost same, but if you can see, the dog is focused here. But if once the dog exits, then you can see these regions gets focused, and this ground is separated from the top, right? You can see that the top is no more existent and the ground is focused. So it has the ability to distinguish between different sections, as we see in segmentation, image segmentation task. And even though it was never trained on image segmentation. So that was a very unique finding of this paper as well. Yeah, so there are costs related to it. This is what I was trying to convey earlier, that the teacher should always be performing better than the student, and which is what they also find empirically in their experiments. So both with those augmentations, they find that even though the teacher is just an accumulation of the knowledge of the student, it always performs better than the student, and which is what makes the whole model works. Yeah, so there are costs related to it, and it's a very heavy cost. I mean, you have to shell out a lot of money to do all these experiments. They have 16 GPU for three full days. So yeah, and those are very powerful V100 GPUs. And they trained it on 300 epochs actually. So this result was for 300 epochs. As I said earlier, that having an image chopped off into 16 by 16 or let's say 8 by 8 or whatever, the information density changes, and that displays on your throughput. So if you want to have more information density per input embedding, then you can process very less data now, right? So if you have to go, let's say your input data is 256 by 256, and you want to go with a pixel embedding, so you want to embed each pixel, then your throughput will really fall back. So you cannot process a lot of data in your given time. This is so I'm working on the implants identification project, and this is what we did. So we took the DINO out of the box from the pre-trained Facebook model, and it was never trained on X-ray images. It was never trained. It never saw the implants data, and we fed in this input data, and this is what it was able to come up with. So it is able to identify where the implants are, though it has never seen the implants. So yeah, so this was something of a live experiment on where you can deploy this kind of architecture in your model. So we are faced with a lot of unlabeled data, very few labeled data, and this is the strategy that we are trying to deploy in our project. Okay, yeah. If you come up with some questions, maybe later on you can. So I created this repo. You can post issues. I mean, questions. These are basically questions, and I do post papers in this repo as well. Some of the papers with some annotations that I find useful. So we can talk over there as well if you have any questions. This is the repo for the DINO paper, and this is implementation, and this is where you can find the paper. So, thank you.